All right, so what subatomic particle are we talking about here? Which one? Electron, exactly. Set the volume. And where's it? Where are they? Where is it located? Electron cloud. You could have said orbital, energy levels, all those different things. We've kind of been drawing it like it is going around the nucleus, kind of like planets circle the sun, but we're going to find out that it's really a little bit more complicated than that as we move through this unit. Left out there. All right, so we're going to start off, and I'm going to show you a video regarding the electromagnetic spectrum that shows different waves that travel around us, around the Earth, and the energy that's involved with that, because it kind of comes back to some things that we're doing with the electrons. So far I've had two that were not that great. We'll give him a try and see what the hell he is.
My name is Joseph Benson. I'm a history and science teacher in Central Illinois, and I've been teaching for an entire year now. I'm obsessed with my students. Being a middle school teacher is so hard to find educational.
Hey, it's Professor Dave. Let's learn about light.
He knows all about the science of Professor Dave explains.
Since we've been able to look up at the sun, we've been aware of light. As darkness is one of the very few things that we instinctually fear, we have always bestowed light with godlike properties. But for all of antiquity, we had no idea what light really was. Figures like Newton and Huygens worked with light in the 17th century, but a more sophisticated description of light, which we call classical electromagnetism, was developed largely by James Clerk Maxwell in the 19th century. This theory depicts light as a transverse wave composed of oscillating electric and magnetic fields, which are at right angles to each other and perpendicular to the direction that the wave moves. We will learn more about these fields later. Just like the kinds of waves we have previously discussed, electromagnetic waves have amplitudes, wavelengths, and frequencies. But instead of different frequencies producing different pitches, like sound waves, different frequencies of electromagnetic waves produce different kinds of light. If the light is visible, these frequencies will correspond to different colors. Frequencies greater than this will exist as UV radiation, X-rays, or gamma rays, and frequencies less than this qualify as infrared radiation, microwaves, or radio waves. All of these phenomena are collectively referred to as electromagnetic radiation, and they can be found on the electromagnetic spectrum. Here we can see all the wavelengths and frequencies ranging from radio waves to gamma rays, and we have found some technological use for all of these in modern society. Even though they seem dramatically different, some requiring things like antennas or other equipment to manipulate, all of them are fundamentally the same thing as the light you can see with your eyeballs. They are just of different wavelengths. All electromagnetic radiation moves at the speed of light, which is about 300 million meters per second in a vacuum, the fastest speed possible in the universe. This is fast enough to get from here to the moon in about a second. And since we know that all waves move at a speed that is equal to their wavelength times their frequency, this product will be equal to the speed of light for any type of electromagnetic radiation. How is it that electromagnetic radiation is produced? To answer this question, we have to learn about electric fields, which are coming up soon. For now, let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
All right. Thank you, Professor Dave. All right. A little bit of our notes. So we're kind of skip around on our notes a little bit today. There's some math equations that we need to do, but we're going to work on those tomorrow. They're not that hard. It's just little formulas that you'll fill in. But let's kind of just start with our background. So starting at the very top with your notes, electromagnetic, or EM, is how I'm shortening it, radiation, are forms of energy which move through space as waves. There's a lot of different types. You saw there those on his electromagnetic spectrum. So there's the visible light, which is only a small portion of the electromagnetic spectrum. That's the one that the wavelength that our eyes can process. There's X-rays. There's UV light, infrared light. We can't see it, but we can feel it. Radio waves, which are manipulated for radio stations. So like when it's 104.5 or something, that has something to do, I'm not exactly for sure, but that has something to do with the wavelength. So most of the electromagnetic spectrum is not visible. So these waves that are going around us, the vast majority of them are in some wavelength that our eyes can't process, so we don't see those. All electromagnetic waves carry energy, and they move at the speed of light, which is c. C stands for the speed of light. So 3.00 times 10 to the 8th meters per second. And we'll use that tomorrow in our formulas. Speed of light is equal to the frequency times the wavelength, and that's called the speed of light equation. So C is equal to frequency times wavelength. Little b for the frequency, and then kind of an upside down y. And like I said, both the formulas that we are using are those ones that you can put in a triangle, save you some algebra. So we would have b and then wavelength. So frequency, which is represented by the v, is a number of waves passing a given point in 1 second, and it's measured in hertz, like the rental car place, or second to the -1, which is just another way of writing 1 over a second, or when your seconds in your denominator. Hertz probably be what we see more. Wavelength, which is this upside down y, I think it's called lambda, is the difference between peaks of adjacent waves, and it's measured in meters or nanometers. When we use this formula tomorrow, we're going to be using C. And if you notice, C has the unit of meters in it. So when we use that formula, if it's given to us in nanometers, we're going to have to convert it to meters. Excuse me. You have to convert it to, if it's given in nanometers, we're going to have to convert it to meters. And 1 nanometer is equal to 10 to the -9 meters. So we'll look at some of those examples tomorrow. Pretty easy to do. The speed of light is a constant. So that means it will not be part of what we think about whenever we worry about our sig figs. And therefore frequency and wavelength must be inversely proportional. And wait a second, I misspelled that. And the V in there, inversely proportional. So if I increase my wavelength, then that's going to decrease the frequency. If I have real long waves, then they're going to have to move slower, and the frequency is kind of how fast they're moving. So those are inversely proportional. Like I said, we're going to skip to these down below the different problems. So we'll go to the top of the back page where you see an electromagnetic spectrum. All right, so if you look here at your electromagnetic spectrum, you can see the different things that we've talked about, some of the different waves. So increasing energy would go this way as it is shown. That would also be increasing frequency. If it's moving faster, it's got to have more energy. So those are directly related. Increasing wavelength goes the other way. So over here, I have really long waves, but they're moving slowly and they don't have a lot of energy in them. On this side, I have these really little small waves. So they're moving faster, their frequency is faster, and that takes more energy. Also notice when you look at these that sometimes you'll have some wavelengths measured in meters, some measured in centimeters, some measured in nanometers. So just kind of realize that, because if you take a number off of this and put it in the formula, you're going to need to be aware of what unit it's measured in. So this little small portion of the EM spectrum is the only portion that has waves in the frequency that we can see. So if we take that little portion and then we spread it out, we can see where the different colors fall. This is red. It has the longest wavelength. And on this side, we have violet. And I'll show you one that's actually in color here. So energy and wavelength are inversely proportional or related. Energy and frequency are directly related. So here is an electromagnetic spectrum with some color to it. So you can see here, this is your whole EM spectrum and just that small portion. So you had already labeled 700 as red and 400 as violet. You have a couple other ones in there on your notes. For the 600, you could put light orange there. And your 500 is going to fall in the green. 500 nanometers is going to be a wavelength that we'll see as green. The photoelectric effect is what we see when light is shown on metals. So this makes metal shine or have luster. So whenever we metals are shiny, we like that. We make jewelry with them. The reason that they are shiny is because the movement of their electrons, and that's called the photoelectric effect. So electrons are emitted or given off from a metal when the light shines on the metal. And that's because light is a form of energy. So if you shine light on metal, you're putting some energy into that, and then that's going to cause the electrons to move. We're going to do it's called flame test lab. It's a fun lab. We'll probably do next week, maybe next Monday, and we'll use Bunsen burners to put energy into different systems and then cause the electrons to move based off of that. So incoming electromagnetic radiation striking the metal ejects electrons. Radiant energy, which is the energy from the electromagnetic spectrum, is transferred in units of energy called photons. When a specific or quantized amount of energy is exposed to the atom jumps from its ground state or the original state where it's usually at to the excited state. So if I just draw a little Bohr model, let's say it had a couple of electrons on the first level, maybe one on the second level. If I put some energy into this system, it's going to cause these electrons to jump to a higher energy level. And then when the energy is given back off, they'll return to their lower ground state. And that movement between those energy levels, whenever they go back to their ground state, it's giving off waves in a wavelength that we can see. It's kind of like the fingerprint of an element. Does somebody want to watch, Elena? Want to wake up, ma'am? Thank you. Okay. All righty. I probably couldn't, yeah. When the excited electron returns to a lower energy level, it releases energy in the form of light. It's kind of like a fingerprint for an element. So when you burn lithium, it should always burn the same color. When you burn barium, it should always burn the same color because the electrons are always in the same electron configuration. So when you put energy into them, then it's going to cause the same movement between orbitals. And that's what we'll do whenever we do that, the lab. They'll burn different colors as we put them on fire. So a photon is a particle of energy having a mass of 0, and it carries a quantum of energy. And a quantum, said twice, sorry, is the minimum energy that can be lost or gained by an atom. So an atom can move between energy levels, but it cannot exist in the middle of an energy level. That's not possible because that's not the package of energy that it's given. The energy of a photon is directly proportional to the frequency of the radiation. If it's having to travel faster, it's going to take more energy. And we'll look at this formula tomorrow. Also, energy is equal to HV, where H stands for Planck's constant. So both of the formulas that we're looking at tomorrow have a constant in them that is used. So once again, if you want to set up your little triangle, that's what your little triangle is going to look like. So on the day that we do the flame test lab, I try to have all the lights off and just a few lamps going on. And then you can also take pictures with your phone if you want to, because some of them turn out pretty cool looking. And this little part of chemistry that we're doing right now is kind of like the physics of chemistry. Are any of y'all taking physics at the same time? No. So definitely not my most favorite part of chemistry and not my strongest part of chemistry, but we will make it through. We don't go too far in depth. All right, so waves and particles behave kind of similar, and electrons kind of fall into both of those categories. So energy travels through space as waves. Sorry. but can be thought, that should be thought, not through, thought of as a stream of particles. Each particle has one quantum of energy. A line spectrum is what is produced from different elements when you put energy into the system as the electrons travel between energy levels. They go from the ground state, which is the lower energy level where they usually exist. It's going to be closest to the nucleus. And then they would go to an excited state. If electrons are put into, if energy is put into the system. So it has a higher potential energy, and you can think of it like neon lights. Energy that's being used with neon lights is electricity, and then that's causing the electrons to move, and then we see that as our bright neon lights that we like. So the Bohr model, which is kind of what we've been using to talk about here, shows that the electrons circle around the nucleus and their different energy levels, and we've been drawing some of those. The electrons can circle the nucleus only in allowed paths or orbits. So kind of like what I said, they can't exist in between energy levels. The energy of the electron is greater when it is in orbits that are farther from the nucleus. And the electron achieves the ground state when the atoms occupy the closest possible level around the nucleus. So that's what we're going to find out as we move forward. The electrons are going to fill up the lowest energy levels first and then go out to the higher energy levels. Electromagnetic radiation is emitted or given off when the electrons move closer to the nucleus. So we see some energy movement or some energy transitions, and these energies of the atoms are fixed and definite. And that's why they occupy energy levels and not just some other random space in between. The energy transitions occur in jumps of discrete amounts of energy, like a little packet of energy. Electrons only lose energy when it moves to a lower energy level. So kind of these things that we've been talking about here at the end are based off of the Bohr model. The problem with that is it does not work for atoms larger than hydrogen, which is pretty much the whole periodic table. And it does not explain chemical behavior. So kind of like the older way of thinking, the older way of us drawing it, and we'll move into something a little bit more complicated. It's called the electron configuration. All right, we're going to stop right there for notes. And if you'll get your Chromebook out. And if you look under in your Google Classroom, excuse me, under second 6 weeks practice, it says practice EM spectrum. And it's in quiz, and you can do it multiple times. This is just practice to prepare you for your quiz on Wednesday over this little portion of the notes. So you have some time to work on that. So feel free to use your notes as you're working through it this first few times or first couple of times.